All right, subscribers, welcome to another beautiful episode of Science with Surbeck. Today we're taking a look at the Unit 1 free response questions for the AP Chem exam. Okay, so this deals with atomic structure and atomic mass, and so we'll get underway with question number 1A. And so it talks about here, the whole question is related to that of K or potassium. And so question 1A says, in terms of the atomic structure, explain why the atomic radius of potassium is larger than that of sodium. Now, there's a couple different ways you could go about answering this particular question, but what I like to think about here is where is the potassium compared to that of sodium? So if you take a look on the periodic table, potassium is one period below sodium. And so how we could go about answering question 1A is by going through this. We could say here that the valence electrons are in a further energy level or period compared to that of sodium. So again, think you've added layers, or you've added that energy level of where those electrons can exist. And so as you add those layers, think it expands as you go through that process. Okay? So now we get to question 1B. It says, in terms of atomic structure, explain why the first ionization energy in potassium is less than calcium. So again, we look at the periodic table, and calcium is just to the right of potassium. But potassium has a lower first ionization energy than that of calcium. Well, what we learned in class, or what I taught you in class, is this. The effective nuclear charge, and I call this ZF, or the effective nuclear charge, is less in potassium compared to Ca, or calcium. All right. Now, what we could also talk about here is this. Because of the effective nuclear charge, the valence electrons in potassium are not as strongly attracted to that nucleus in potassium. And it's all because, again, think that pulling power. The more protons you have, the more pulling power it has, the closer those electrons become. The closer the electrons are to that nucleus, the harder it is to pull that away. All right, so let's go ahead and let's look at part D. So how about C? Part C says, potassium forms the compound K2O, which has the ionic properties that are brittle. Identify another element M that is likely to form a brittle ionic compound with the formula M2O. Justify your answer in terms of periodic trends. All right, so periodic trends. Remember, elements in the same group or family are going to tend to react the same and they're going to tend to behave the same. So if you find potassium, it's in group 1. Any group 1 element will do. So I'll put here for 1C, any group 1 element. And our example here could be Na2O. And the reason that it could react the same or be the same type of compound or have the same similar type of properties is Na is in the same group as potassium K. Okay, so that would be the answer to C. Okay, so moving on here to 1D. It says the compound K2O2 also exists. And a chemist can determine the mass of potassium in a sample of known mass that consists of either pure K2O or pure K2O2. So the question is, can we determine which compound is in the sample? Indicate yes or a no. Well, yes, chemists can do a lot, and we can definitely do this here. And so our answer here to 1D, is yes. Yes, as long as the percent mass of potassium is known and can be calculated. And on top of that, the percent mass of the entire compound is identified. So we have to know the percent composition of both compounds, and we have to know the percent mass of K from whatever sample that we're working with. All right, so that is the completion of part 1 of this question. All right, so part 2 is a different question. We actually have a chart that we have to answer, okay? So the chart here deals with this particular portion. Let me adjust my paper, and we go from there. It says a sample of a pure element is analyzed using a mass spectrometer. The results are shown below, and it's seen in this table. And so the question 2A says how many different isotopes of the element are in the sample. Well, number of isotopes is going to be represented on how many atomic mass was found, or how many atomic masses were found. So because we have 3 different atomic masses, there is 3 different isotopes. So all we need to do is answer 3 isotopes. Okay. Now, with this here, it says part 2B, describe how this information can be used to calculate the atomic mass, or the average atomic mass of the element. So for this here, I'm going to write the formula, is we need to, for each isotope, so we'll say each isotope, what we need to do is this. We need to take the percent abundance times the atomic mass. Once we do that, we add all of the isotopes' individual mass that they contribute, and we identify the atomic mass, or the average atomic mass. So for this here, keep that chart handy as we will utilize some information. But for question 2B, how we would do this is this. I would look at that first mass that is given, and it has that 24 column, and you go up and it just barely touches that 0.8, or just is barely below it. And so that is 79% of that isotope. Now, percents aren't very helpful, so what I'm going to do is I'm going to divide this by 100, and I'm going to get 0.79. And I'm going to multiply that by the atomic mass that's seen there, and that is 24 AMU. Now, I'm going to go ahead, I'm going to calculate this because we're going to need this in a second, but we have 0.79 times 24 AMU, and that gives us 18.96 AMU. Now, the next percent abundance here, we shift over to that next bar on the graph, and we see here that there is 10% abundance. The percent doesn't really help us, and that gives us 0.1, and that mass right there is 25 AMU. So again, I turn to my calculator here. I had put 0.1 times 25, and we end up with 2.5 AMU. Okay. Now, the last percent abundance is 0.11, or 11%. We divide that by 100 to give us 0.11. We multiply that by the mass that's seen for that isotope, which is 26, and we go through the calculation in a similar format. So we get 2.86. Now what we need to do is add all of these together. So I'm going to add 18.96, 2.5, and 2.86. So 18.96 plus 2.5 plus 2.86 gives me a mass, an average atomic mass of 24.32 AMU. Okay, so that's how we would go about showing how we would calculate it. And obviously we went ahead and we calculated it. And part C here, I'm just going to show this, it says identify the element. Well, the element here, if you look on the periodic table and you find something with very, very close atomic mass to 24.3-ish, give or take a few 100ths, you'll find that the element is Mg, or magnesium. And so that is our element. Now, our last part here deals with the electron configuration. It says here, write the ground state electron configuration of an atom of the element you identified in that previous part. Well, remember, it may be good to review the electron configuration, but how we would do that is we go through each subblock and we write that electron configuration. So we'd have 1s2. We still haven't got to magnesium, so we'd need 2s2. We then move over to 2p6, and then we would get to our element in that 3s block, and it would be the second element there, and it would be 3s2. All right, so that is how we would go about answering these questions on atomic structure for these particular examples. Hope you have enjoyed this particular question. Hope you have reviewed or remembered a lot that we've done throughout the year.